Okay, we're about to start Unit 2C, the second part of the lesson. This is the homework results or answers if you did the first part, 2C. We're talking about the least squares regression line, some more about it. So it's the line that makes the sum of the squared residuals as small as possible. We'll see a picture of that will make that sense, make more sense. So we calculate x bar mean. These are formulas you need to know. Well, actually, they're on the formula sheet. I should say you don't have to know them. I want to mention and talk about this a little bit more. We'll come back to these when we need them. You will need these. You will need these for sure, and they're on the formula sheet. Okay, a random sample of 15 high school students was selected to investigate the relationship between foot length and height in centimeters. You would think there might be maybe a positive relationship between if you have a longer foot, maybe you're taller. Certainly possible. The mean of foot length is 24.76 with a standard deviation of 2.71. The mean of the height is 171 with a standard deviation of 10.69. So for these formulas, you need the means of the x and y variables and the standard deviations of those. Correlation is r equals 0.697. Calculate the equation for the least squares regression line for predicting the height of foot length using this data. So I'm just going to show you how you might use these formulas. So it says that B is equal to R. So B equals R, which is 0.697, times a fraction, the standard deviation of Y, which I think is heights here, so 10.69. Divided by the standard deviation of x, which is 2.71. So we should be able to use our calculator to figure out what b is. So you would type in 0.697 times the fraction, 10.69 over 2.71. Now we know b is 2.749. 2.749. So now we're going to plug into this formula. Again, y bar and x bar are averages, right? So if you look at the data here, so we've got y bar, the average y is 171.43 equals a, which I don't think we know, but we do know b is 2.749 times the x bar, which is 24.76. So if we did this right, we should be able to solve that equation. So use the solve command. 171.43 equals a plus 2.749 times 24.76. Comma a, the variable we're solving for, we get 103.365. 103.365 is equal to a. So now I think we have enough to write our equation. So y hat, which in this case is height, equals a, which is 103. We'll see if we did this right in a second. 365 plus b, which is 2.749 times x variable, which is foot length. Something like that. So let's see if we got it right. Let's see if they did it. They said B was 2.75. Did we get that far? Yeah, we did. Okay, I think we did a few more decimals. That's okay. They said A is 103.34. That sounds about right. Ours is probably more accurately rounded a little bit more. So y hat, I like the way I rewrote our equation a little bit better there, just because I used the variables in the equation, which is just better, just smarter. You don't have to define the variables then. It just saves you time on the AP test. Okay, displaying the slope of y-intercept after report. There's no firm rule for how many decimal places. Go, decide based on the context. Go at least to the 10th, maybe the 100th, sometimes 1,000. It kind of depends on the setting. Okay, so this is new. So this is computer output called Minitab. It's a computer program that crunches all the numbers for us, gives us all kinds of data. And so those are the two you have to know in the right spots there. So it's kind of hard to understand. So I think that next to the word constant is the slope. So I think of constant as a slope there. So 38257. Below the y-intercept, I'm sorry, next to the constant is the y-intercept, if I just said that wrong. Next to the y-intercept is the constant. Below the y-intercept is the slope. And it's below the word coefficient. The second column there is standard error of the coefficient. So we don't need that one, and we don't need T or P for these guys at all. The other ones we might need down there at the bottom, that S is standard deviation, I believe. R squared, you're familiar with, maybe at least if you take the square root of that, you would get R. Well, kind of. It wouldn't tell you if it's positive or negative. If the slope is negative, which here is, you would have to take the negative of the square root of that to get R. So it doesn't tell you the direction, but it tells you what the number R is minus whether it's positive or negative. Don't use R squared adjusted. We don't use that. But the two main ones you need are the y-intercept and the slope, which are labeled there. For now, that's all you need, really. I was just talking ahead there. Okay, so random sample of 15 high school students select to investigate the relationship. Here's the output, right? So then this is what you do with that. So you go, okay, so let's look at this. So I know my equation is y hat equals a plus bx. In this case, we're predicting height. So height hat, or predicted height, is the y-intercept, which should be the next number next to constant, 103.41, plus the slope, which is 2.7469. You could round that if you want to. You could also just write it times the foot length. That was written really sloppily, but that should be the answer there. Let's see what they did. Oh, they wrote it the way I like too. Good. And you can round. That's totally fine. Best idea to use the variable names there instead of y hat and x. I think it's a great idea for the AP exam tip. I do that. So let's type the data into our calculator here. So it's going to take a minute. I'm going to do that off to the side. Okay, so it took a bit of doing, but I typed all of that into my calculator. So we're going to calculate the least squares regression line. I'm going to do it a couple different ways. So one way is on a calculator screen. So if you had a calculator screen, you can hit menu 6.1 and then go to A plus BX linear regression and choose your X list, which I think was miles. And then your Y list, I think, was price. And it automatically saves the equation in F3, which is kind of handy. And so it just calculates it for you, gives you R and R squared there, gives you the regression equation by giving you A and B, it gives you the form, and it gives you residuals. If you wanted to see the residuals just for fun, variable resid should be stored as, so those are the residuals if you wanted to see them. I don't think you need those, but that's what that resid means. So you have your equation that way. Much preferred, just go to Data Statistics page, choose your X variables, miles. We'll get a picture of this as well, which is really nice, of the scatter plot. Go to price. Okay, you can see it's a downward trend here, pretty strong, or at least moderately strong here, I think. So go to Analyze, menu Analyze, Regression. Go to A plus BX. It puts it right on the screen. And mine actually gives me not just the equation, but also the R squared value. To do that, if yours doesn't, go to Menu, Settings, and click Diagnostics. If I don't have Diagnostics on, it doesn't show me. But if I go Menu, Settings, and click the Diagnostics button, now it shows me R squared, which again, R squared is 0.6642. So if I go to calculator page and take the square root of that number, 0.6642, I almost get R. Well, sometimes I get R. I got 0.814, If you look back at the previous screen, you can see that R is actually negative 0.814. Because the slope is negative, R squared, if you take the square, it's always going to be positive. But because the slope is negative, R has to be negative because it's going to have the same kind of association. So you have to kind of look at the slope to find out whether it's positive or negative. But you can get it from that screen as well. Also, anytime, this is kind of interesting, but anytime you ever do regression here on this page, if you go and add a calculator page, not a scratch pad, but calculator page, and hit the variable key, if you go down to stat R and press enter, it'll give you the R value. You don't even have to take the square root. It just tells you what it is. It automatically does that whenever it does regression. It doesn't always show you the value if you're on the data statistics screen, but it does do that for you. Let me go back to, I'm sure they're going to talk about this later, but I'm just going to go back to it. The definition of least squares is the sum of the squared residuals as small as possible. So let's go back to our graph here. I'm going to go control left arrow to turn the page. Okay, click off there. Okay, so if I hit menu, it's kind of interesting we can do this. I think it's under analyze residuals. Let's go there. I'm going to show residual squares. Oh, it's kind of interesting. So what that is the vertical part of one side of each square there is actually the residual. But they made a square out of each residual. So if it's a long residual, it's a pretty big size square. If it's a smaller residual, shorter residual, it's a very small square. But they made squares out of all of those. If you sum up the area of all those squares, so in other words, we're trying to get it so that all the points are pretty close to the line. If it's pretty close to the line, it's smaller squares. So we're trying to draw a line so that all those squares are pretty darn close to the line. And so that is called the residual line. It does do something interesting too. And I'm going to do this again, just for your understanding. I think it'll help. So I'm going to go menu. I think it's under actions, analyze, plot value. So I'm going to do this. I'm going to do the mean of miles. It's going to plot a value. Do you see that? It looks almost in the middle-ish, but it's the mean of the x values. I'm going to do this now. Menu, analyze, plot function, and I'm going to say the mean of price. So the mean price is going to draw a horizontal line there. And I don't know if you notice this, but do you notice those two lines cross on the line? That is not an accident. That point is called the x bar, y bar point. It's the average x and the average y, where those meet. Always, 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 the regression line has to go through that point. So I'm trying to show you understanding with that, because that's where that formula, when we look at this formula here, do you see the second formula? It says y bar equals a plus bx. We're basically taking the y equals mx plus b, plugging in the average y number and the average x number, because every regression line goes through that exact point. So we know it's going to go through the x bar, y bar point, so we can use that equation. That's where that formula kind of comes from, if that makes sense. Okay, so we did that. Okay. So a residual plot is a scatter plot that displays the residuals of the vertical axis and the values of the explanatory variable on the horizontal axis. So you can actually do this in your calculator. Let's show you this. So I'm going to undo some things here. Okay, so that's a little bit better. So I'm going to hit menu, analyze residuals, and go to residual plot. It actually does this vertically. It's actually right underneath where it's supposed to be. So you can see those points are actually the points, but it's almost like they flattened out the line. And so now we can just measure the vertical distance to each one of those points. So we don't have to kind of like, I don't know, their line is just kind of like, it's kind of flattened out. Now it's easier to see the spread the points make. It's called the residual plot. So when the line is at y equals 0 there, it's points all about it like that. That's a residual plot. It's going to have that look to it every time. And you can see that where those points are, and they're kind of spread out apart from the line about the same distance they are from the slanted line there. So it's just a different way of viewing those points. This is the formal definition of that. notice we're measuring the vertical values there. So if you took this graph on the left and made a residual plot, you can see that those outlying points on the right there are now kind of above the line, but they're still outlying kind of points there. Maybe fit the pattern, maybe don't. There's at least one point that doesn't fit the pattern there. But it just has a different view of the residuals, and just really looking at the residuals in a way we can see how close they are to the line a little bit easier than we can with the original plot. And we have to look for patterns. Oh, so this is cool. So the U-shaped pattern, the curve shape in the residuals indicate that this is not a good linear fit. So this is really why do we do residual plots? It tells us if it's a good linear fit or not. So if you're not sure, and sometimes you will not be sure, you want to look at the residual plot. It kind of confirms, oh, this is a good linear fit, or it's not. What we're looking for, you might go, well, what are we looking for? Look at this data on the left. Does that look like a good linear fit there? Just the eyeball test? I'd say it does. It looks negative and moderate or moderately strong. I'm not sure. If you look at the residual plot, it's very scattered. So the scattered, there's no curve pattern. Because there's no curve pattern, we can say this is a good linear model, a good linear fit for the data. So if the pattern in the residual plot is scattered, that is exactly what we're looking for. We want points all over the place. That means it's a good linear fit. So determine what it is. If it shows random scatter, linear fit is good. If it's a curve pattern, you are not doing, linear is not the way to go with this one. So that's the basic idea. If this is a residual plot, is that a nice curve pattern there? I see a curve pattern. Is the linear model appropriate? I would say no, that is not appropriate, right? Residual plot on the left is not appropriate because there's a U-shape, there's a curve pattern in the residual plot. Okay, so finally we're learning about this thing called R squared, called the coefficient of determination. You might want to remember that, just it comes up every once in a while. It measures the percent reduction in the sum of the squared residuals when using the least squares regression line to make predictions rather than the mean value of y. It measures the percentage of the variation in the response variable that is accounted for or explained by the explanatory variable. Okay, so we'll come back to that in a minute. I think the standard deviation of the residuals, S. Oh, so S is the standard deviation of the residuals. Measures the size of a typical residual. Remember, standard deviation is the typical difference from the mean. In this case, a typical length of the residual, basically, right? So the use regression from any tab to answer the question. So how does the residual plot indicate about the data? What is it? So it's a random scatter, so the linear model is a good fit. That's what it says. Okay. Interpret the coefficient of determination, R squared. So I think of this, so R squared is 69.7 there. So it's almost like a script you memorize for R squared, the coefficient of determination. So I'm going to try it my way, and then we'll look at what they say. So something to the effect of 69.7% of the variation in X, in this case, X is handspan, I think. Putting a blank there because whatever X is, can be explained by the variation in Y, which in this case is the number of starburst. Let's go back to, and look, before we look at what they have here, look back at the formal definition. It measures the proportion or percentage of the variation in the response variable, Y, in other words, that is accounted for or explained by the explanatory variable in the linear model. I think I forgot to add the words, I probably should have said, in the linear model. That would have been even better. linear model. So that's basically your script here. So let's see what they wrote, because it's probably better than what I did. That one. About 69% of the variation in Y, or number of candies grabbed, is accounted for by the least squares regression line with X equals a handspan of, so it's accounted for. So I think I might have modified that. I forgot, they started saying it more this way. So it can be explained by the variation, and so in the linear regression line, linear regression line, I think is better to say there, something like that. You can say slightly different versions of this, but it's got to sound something to that effect. Again, it's kind of like a script to memorize there. I like the way they said it too. The coefficient of determination is displayed in the middle of the bottom row as r squared, right? That's what we said it is, okay? Interpret the standard deviation of residuals. So that number at the bottom left there, that S equals 4.0342. So I'm going to try this. I don't know if this could be good. We're going to try and look at the correct answer here. So 4.03 is the typical residual length. Let's see what they said. The actual number of camels is typically about 4.03 away from the number predicted. Oh, I like theirs, it's better. Let's go back and look at the definition first for a second. Measures the size of a typical residual, the typical distance between the actual Y values and the predicted Y values, which is the residuals, by the way. I guess you don't want to define necessarily, I was kind of defining it with the word residual, like with a residual, whereas they're actually saying the residual is the distance between, typical distance between the actual and the predicted Y values. So I was using the residual in the definition there, or in the interpretation there. So it's probably better to say it this way. Actual number of candies grabbed is typically about 4.03 away from the number predicted by the least squares regression line. So the actual, that vertical distance there is typically about 4.03. The residual is about 4.03 away from the regression line. It's S, it's called the square root mean square error. Oh wow, okay. So that's the lesson for today. There's a few more questions here if you want to do them. I'm going to show the question. Those are the equations you plug on all those things, and you get the answer. Don't be afraid to use the solve command there if you need to. This one, hopefully you can recognize which one to get the equation, which one the y-intercept is 154.999, the slope is negative 2.757, and then you write your equation. I would prefer if you wrote it with the acceleration as your x there, I think. And so this is probably measuring the stopping distance would be y there. So use those words and for y and x instead. Little hint there, acceleration, the number next to the slope is usually the x value there. So that helps me sometimes just to know that. The word, I should say, the word next to the slope, to the left of it, acceleration is the x value. And usually you have to read the problem to see the y value, but it helps to know that. This one, use the residual plot to determine, is it appropriate? That's pretty scattered. Yes, definitely the linear model is appropriate.